All right, here's another example calculating the volume of a solid of revolution using the disk or the washer method, which is 6.2 in our book. What's going to be different in this example and the next one it'll turn out is we're going to switch our variable of integration. You're like, how in the world do you know you're switching your variable of integration? Well, let's start out with an example. Suppose I first asked you to find the area bounded by these two curves. So I sketched that ahead of time. Desmos can do a much better job of graphing these than I can, but I thought it might be nice to have a couple of pictures in your notes. So I tried to sketch this here. It took me a lot longer than you'd think, even though it doesn't look all that good. We have these two curves. In green, we have y equals the natural log of x. And then in blue, we have this linear function. So that straight line is right here. And you can see from the picture that those two curves bound this region, which I guess I could fill in. And so far, everything is identical to what we did in the previous videos. What's going to change is we're no longer going to take this bounded region and rotate it around the x-axis. And you're like, yeah, we didn't do that in one of the other videos too, right? We rotated around y equals -2. Well, we're going to switch things. We're not going to rotate it around any horizontal line. So not y equals -2, not the x-axis, not any other horizontal line. What we're going to do is we're going to rotate this thing about the y-axis. And you're like, yeah, whatever, some other line. What do I really care? How much could that possibly change? Well, look at what happens. Our y-axis is this vertical line right here. So if we take this shape and we rotate it around this axis, maybe you can kind of picture the solid that would result. If you could, that's great. And if you can't, me adding more and more to this picture probably isn't helping any. But the idea is I'm going to take this and I'm going to rotate it around the y-axis. And what it'll kind of end up looking like is this right here. I know it's not a great picture and maybe this doesn't benefit anybody at all, but the point is we're going to have a very different looking shape than we had in the previous videos because we're rotating around a vertical axis instead of a horizontal axis. So what's the takeaway? What's this thing kind of end up looking like? I can't really tell from your picture. This is a different region than the region that we have bounded, but maybe it's close enough that you can kind of get an idea about what our solid will look like by taking a look at what the solid will look like if you rotate this region around the y-axis. It's a little bit slow, but you can kind of see this thing start to grow as we take this region and we wrap it first behind the y-axis and then all the way around so that it meets kind of back up over on the other side of our y-axis and then it finally makes its way all the way back to where it started. The point is just we're going to have this different looking solid that we need to figure out the volume of. But you might already notice some similarities. Whereas the solids in the previous video kind of looked like cups laid down on their sides or tubes laid down on their sides, this one sort of looks like a cup sort of sitting upright or a tube kind of sitting upright. In fact, if you kind of turn your head 90 degrees to the side, this looks a lot like what we did in the previous video. Oh, that makes a lot of sense because really the only difference is the axis we're rotating around. And if we switch from the x-axis to the y-axis, we're kind of just changing the orientation of our picture. And that'll allow us to figure out this volume in a pretty similar way that we did the previous volume. The previous volume, what we did is we picked on an x value and we took a vertical slice. And that vertical slice, it took us a little while, but maybe by the end of the videos, you were able to see that, oh yeah, each vertical slice is going to be a washer. Well, there's a problem. If you take a vertical slice here, you're not going to end up with a washer. What are you going to end up with? I don't know, some weird conic section that would be really hard to describe or visualize. Don't even worry about it because you don't want to take vertical slices here. You don't want to take vertical slices because anytime you rotate around a vertical line and you're figuring out the volume using either the disk or the washer method, what you're going to do is take horizontal slices. Because the nice thing about a horizontal slice in here, any slice that you want horizontal, it'll just be a washer. And that might take a little while to convince yourself of, but if you were able to convince yourself that vertical slices in the previous videos were washers, maybe you can see that horizontal slices in these videos are washers. Much like the previous videos washers, these washers have an inner radius and the outer radius, and just like in the previous examples, those radii are determined by these two different curves. What's going to be different is now for an arbitrary y value in here, if I pick one at random, I don't know, right here, I could talk about the outer radius of the washer as the distance not from the x-axis to this curve, but instead from the y-axis to this blue curve. If you can tie together in your head the length of this blue line representing the same thing as the length of this blue line, the radius down here for the washer being the distance from the x-axis to this curve, then you kind of have the theory of everything that we need to be able to do. Similarly, the distance from the x-axis to the green curve is going to represent the length of the inner radius of this washer. And I guess I'm picking a specific x value, so this green and blue line should be right on top of each other, but I just thought you might not be able to see the color, so I just wrote them really close to each other. At any rate, all we're going to do is we're going to calculate the volume of one of these horizontal washers, and then we're going to add up infinitely many of these washers and kind of stack them on top of each other as opposed to stacking them side by side. We'll stack them on top of each other to fill up all of the volume from here all the way up to here. The volume of the washers down towards the bottom and then again up towards the top are smaller than the volume of the washers that are more in the middle. The volume of the washer is determined by the y value now. And so because it's determined by the y value, we're going to integrate with respect to y. My setup will be pretty similar. I just have to figure out when I'm creating this volume, what two numbers do my y values span from? Well, you might look at these 2 points of intersection and be like, oh yeah, this point has an x value of 1 and this point has an x value of e. That's 100% true. But it's not relevant. We don't care about the x values of this bounded region. We care about the y values. So what you want to do is look at this point and not see a 1, but instead see a 0. Not see the x, but instead see the y. Similarly up here, you don't want to see an e, you want to see a 1. What I'm saying is the picture seems to imply that our bounds of integration will go from 0 to 1 and will integrate with respect to y. You can calculate those bounds if you solve each of these two equations for x and then set them equal to each other, and then you'll get an equation involving just y's and numbers, and you can solve that equation for the numbers, and the numbers should end up being 0 and 1. It turns out that that equation will be really hard to solve. It'll be kind of a mess. So maybe instead we can just verify that 0 and 1 are really the y coordinates of these 2 points of intersection. If we put 1 into these two equations, the natural log of 1 is just 0. So this graph definitely goes through the point 1, 0. If we put 1 into this equation, 1 minus 1 is 0, and 0 times anything is 0. So this graph also goes through the point 1, 0. So this point 1, 0 is definitely on both graphs. What I'm saying is the lower bound of integration, its y coordinate should definitely be at 0. What about this point up here? Well, the graph seems to imply that when the x value is e, the y value is 1. Over here, the natural log of e is exactly equal to 1. So this graph in green has to go through the point e, comma 1. And then over here, if I change all the x's into e's, this would be e minus 1. But e minus 1 times 1 over e minus 1 would just be equal to 1. So this graph goes through the point e, comma 1 as well. What I'm saying is this point right here is on both graphs, and it's got an x value of e and a y value of 1. And all I care about is its y value, which is this 1 over here. What I want to integrate is the volume of an arbitrary washer in between these two bounds. And the volume of the washer would just be pi times the outer radius squared minus pi times the inner radius squared. And so if I could represent my outer radius, my inner radius in terms of y, and that's really important because my variable of integration is y, I could just integrate this thing and be done with the problem. Well, to solve this equation for x, it's easy enough. If y equals the natural log of x, then I just do e to both sides of the equation, and I can get x equals e to the y power. Similarly, for this equation right here, if I wanted to solve it for x, well, maybe I could first multiply both sides of the equation by e minus 1. And then I just have to add 1 to both sides of the equation, and I'd have the x all by itself. X equals y times e minus 1 plus 1. And maybe you can kind of see if I set these two equal to each other to try to solve for these bounds as opposed to just verify them, I'd get e to the y equals y times e minus 1 plus 1. And I'd be like, and then what do you do? And I don't even know how to solve that. You'd probably have to involve logs somehow to get this out of the exponent. But if you took logs on the left and logs on the right, this thing would kind of blow up and get really ugly. I'm sure there's some clever algebraic way, but I got to be honest, I don't know what it is. So we're not going to bother with that. All we're going to do is say, all right, this represents the radius of the inner circle, and this represents the radius of the outer circle. So for my integral, I'll replace this capital R with this expression. And then I'll replace my little r with this expression right here. And hopefully the resulting mess will be something that I could take an antiderivative of, because then I could evaluate this and be done with the problem. And I think it all does work out that way. Let's see, maybe first we pull the pi's out in front, because they're just constants like they always are. And then foiling these parentheses will be a little bit of a mess. There's different ways you can do it. I think what I'm going to do is I'm going to view this entire thing, y times e minus 1, as my first term, and this 1 as my second term. And then if I think FOIL, y times e minus 1 times y times e minus 1 would give me y squared, and then e minus 1 squared. That's the f in FOIL. And then the o and the I in FOIL I would get by doing 1 times this expression, but it would happen twice. So I'd have 2y e minus 1. And then the L in FOIL would just be 1 times 1, which is this 1 here. And then from that expression, I want to subtract e to the y squared. Well, a nice thing happens when you raise exponents up to exponents like I'm doing here. I can just multiply those two exponents together. So I can refer to this as e to the 2y. And what you'll see is referring to it as e to the 2y will make life a lot easier when I have to take antiderivatives later on. This looks really ugly, but I don't think it's going to be nearly as bad to integrate as maybe you're expecting. And the reason why is over here, even though this is a huge mess, e minus 1 is just some number. E minus 1 squared is just some number. This is just a constant. I know it doesn't look like a constant. It looks like an expression, but it's not. It's just equal to some number. And when we're integrating, constants are really easy to deal with. You just leave them alone. So that e minus 1 squared, I'm going to treat it like it's the number, 7 or something. Just completely leave it alone. And then the antiderivative of y squared would be 1/3 y cubed. Similarly over here, the 2 and the e minus 1, those are all just constants. They might not look like constants, but they are constants, so I can leave them alone, treat them as constants. The antiderivative of y is 1/2 y squared. The antiderivative of the 1 here is easy. That's just my variable y in this case. And then the antiderivative of e to the 2y power, well, it's almost e to the 2y power, but if you took the derivative of e to the 2y power, then you would get e to the 2y power times 2, because you'd have to use the chain rule. So I'm going to toss a 1/2 down in front here to make all the coefficients line up. You could also do a u substitution where u is equal to 2y if you felt like it. I think this is the antiderivative of this mess, so this is what I'm going to have to evaluate from 0 to 1, which were my bounds of integration, which I left off on the line above. Nice thing about plugging in 1s and 0s is it usually works out pretty nicely. If I first go through and plug in 1s, 1 cubed is 1, 1 squared is 1, y is 1, this is a 1. So this first term, I just get the e minus 1 squared times 1/3, which I could write this way. From the second term, since 1 squared is just 1, that goes away. This 2 and this 1/2 cancel out, so I just get an e minus 1. From the third term, changing my y into a 1 is as easy as writing a 1 right there. And then changing my y into a 1 here, e to the 2 times 1 power is just e squared. So I have 1/2 e squared. Unnecessary parentheses just to kind of show to the reader that I got this from evaluating this expression at 1. Now I want to subtract what I get when I evaluate this expression at 0, which will work out even easier because 0 cubed is 0, so this entire thing is 0. 0 squared is 0, so this whole thing is 0. This is a 0. I kind of get 0 plus 0 plus 0, which you don't even have to write if you don't want, minus, if y is equal to 0, 2 times 0 is 0, e to the 0 power is 1, and 1 times negative 1/2 would be negative 1/2. Now I go cleaning things up. I think I'm going to want to expand this out at some point, so I'm going to FOIL e minus 1 squared. This is optional, I would say. E squared minus 2e plus 1 is what you get, and that whole thing is over 3, because note the 3 wasn't squared, just the e minus 1 was squared. And then this e, there's nothing I can do, but this negative 1 and this positive 1 cancel out, and then I have 1 minus 1/2 e squared, and then I'm subtracting negative 1/2, which is the same as adding 1/2. Combining some like terms, I'm going to break this up into 3 different fractions. I have 1/3 of e squared, which is the same as e squared over 3. I have negative 2/3 of e, and then I have 1/3. And the reason I wrote it in this form is maybe that'll make it easier to combine with this e, this minus 1/2 e squared, and this 1/2. All that mess needs to get multiplied by pi, which I'm moving from the left side to the right side just because I feel like it. 1/3 e squared minus 1/2 e squared. I want to look at sixths. This is 2/6, this is 3/6, so I end up with negative 1/6 e squared. Negative 2/3 of e plus 1 whole e, which is 3/3 of e, would be 1/3 e. And then 1/3 plus 1/2 ends up being 5/6, because this is 2/6 and this is 3/6. You could write this in lots of other forms, but I'm satisfied that this is pretty enough. Really, you could have stopped several steps earlier if you didn't feel like doing this algebra. I always do this algebra because I feel like even if it's mostly arithmetic, these algebraic skills, if you practice them a whole lot, they get better and better, and then when you need them, it's a little bit more natural.